What do we got? What's going to happen, Hamish, if I put them in together? Yep, they'll reach thermal equilibrium. They will reach thermal equilibrium. They'll actually mix all together evenly, won't they? And if they reach thermal equilibrium, what laws am I talking about? The zeroth law. The zeroth law says that that will reach thermal equilibrium. It will also flow from the hot to the cold. Which one was that one? The second law. Right on. What about if I do this? What about if I go in a hot metal cube and I put it in the beaker of water? What's going to happen, Logan?
The water will take energy off the cube.
Right. I like the way that you just said that. What Logan has said is that the water will take energy
The water is a cold substance. So
from the cube. I could say this would be the water, and it's going to, this will be the cube, and this will be the water. The water is going to lose energy to that cube. Would you agree?
Yep.
Should they be equal?
Eventually.
I'm saying in total value, should that equal that? Jimmy's nodding.
Wouldn't it equal the sum of those?
I would argue that this, actually,
Yeah, that's zero.
the change in those, the difference between those two energies should be zero, shouldn't it? When would it not be zero? Huh? Can't hear you type.
At the beginning.
Not at the beginning. One of these is going to actually be a negative, isn't it?
Yeah.
Right. The water is going to gain energy from the block. The block's going to lose heat. It's going to give it to the water. The water's going to increase in temperature, but the overall energy should be equal to zero, unless energy is coming in from the environment or it's losing energy out of the beaker to the environment. But again, we're just assuming this ideal system that nothing's changing. The amount of energy that comes in. Let's get rid of the negatives for the moment. We're going to solve this in two different ways. Assuming we're going to say that the amount of energy given up by the metal. Why did I put C?
Cube.
Oh, okay. Let's say metal. The amount of energy in the metal should be equal to the amount of energy gained by the water. That would be a fair assumption, provided no energy is lost and no energy comes into the system. Okay, so let's have a look at some of the problems. Get that question down, please, and let's go and solve this. 50 grams of water. All right, so this one here is not a metal cube. This is actually just two quantities of water. We've got 50 grams at 25 degrees and 100 grams at 90 degrees. I'm going to give you maybe a minute or so just to talk to your neighbour about how you think you might go about starting to solve this problem. I haven't taught you any of this yet on how to do it. See if you can start making up a bit of a plan of how you might go about it. Go.
Even if they were the same temperature.
And what is heat in the formulas we know what that is for heat.
So we change cold water to black.
So the Q of one water has to be different from the Q of the other. You mix them together and then try and figure out the temperature. What have you got that's adding conditions? Right on. We might have a look up here. Does anyone have a bit of an idea of what they think we might be going to do here? I saw Jimmy leaning over talking to Jake. Do you have a bit of an idea? Go, Jimmy, talk to me.
Alright, so I would probably compare the heat of the 100 grams of water at 900 degrees to the temperature of the 50 grams at 25 degrees and divide them out between each other.
Okay, so you're sort of saying that, and similar to what Jonas was just saying now, we're saying that that water there, and I'll put that maybe in brackets, that water has an amount of energy,
Yes.
has an amount of heat, Q. We also have another 100 grams at 90 degrees, and that's also Q. It's got its own amount of energy, and if I mix them together, what am I going to end up with? The energies together, so I'm going to get a different temperature, right? Well, that's what we're trying to figure out, the temperature. If I mix them together, is it going to be halfway? You reckon that might be halfway between 25 and 90 degrees?
If they're the same grain.
Say it again?
What if they're the same mass?
If they're the same mass, and not just the same mass, but...
One's less mass than the other.
Right, so this one's only half the mass, but what else is different about those two? Alan? They're different masses, but there's something else that's different about those two. The temperature.
That was too obvious.
I know, right? Sometimes we ask obvious questions. Well, this one's only at 25 degrees, so the amount of Q in here, the amount of heat in this solution is significantly less than this one. There's a lot more particles moving around, and they're all moving a lot faster on average. So if I mix them together, it stands to reason that when I put them together, they're not likely to meet halfway between temperatures, because there is so many more of those particles than these ones. Well, in a sense. So what we're going to do, well, we know with the, if we're dealing with Q, what formula? Jake, and ask you because you're not looking. If I'm dealing with Q, what formula am I likely to be going to use? Okay? Latent heat. So I've got a latent heat formula. Do I have the latent heat of vaporization? Did it vaporize? Did it turn to steam in this problem?
No.
Did it melt during this problem?
No.
Did it freeze during this problem? Did it condense during this problem?
No.
I'm not going to use latent heat.
Damn it.
What other formula do I have that deals with Q?
Q is equal to MC delta T.
Ooh, so do I have M?
Yeah.
Do I have C?
Yes.
No, I don't.
Yeah, we do.
Yeah, I do. We just know it, don't we? It's like 9.8 gravity. We just know it.
I just can't get in that door.
We have M. We know what C is. Do we have a change in temperature? No. Stomp your foot. Huh? Rather not.
What about in the dust?
Okay, but we do know sort of delta T. We know a bit of it. We know this. We know delta T is actually the final minus the initial temperature, correct? Oh, hang on. I know that. Yes? Do I know this? I know what the final temperature is. That's what I'm trying to figure out. Now I've got one variable in there that I don't know. On the other side, Q equals MC delta T, well that's TF minus TI. I know the initial, but I don't know the final. I've only got TF to solve for, but it's a little bit of a trick in here now. I'm going to solve it two ways. We'll solve it this way first, and remember, back up here I said Q is equal to negative Q. So we're going to put in here negative MC delta, whoops, I left out my C. MC delta T. I'm going to do it that way first. That Q is equal to the negative Q. One's giving up energy, one's taking in energy. When we did delta U equals Q plus W, or Q minus W, depends whether the work's coming in or the work's going out. Now the work's going in or the work's coming out. The Q's going in, the Q's going out, so it's a positive or a negative. So let's set this out a little bit better, shall we? We're going to say Q, and I'm going to call this one here, does the water gain or lose heat? Gains. So I'm going to put this Q gained. Whatever, so I don't care what subscript you use, but I'm going to put QG, because that's the Q, that's the energy that's gained, is equal to MC TF minus TI. Sorry, let's get rid of that Q. Sorry.
Huh?
Well, I'll say this is Q, isn't it? saying the whole thing is Q, is equal to MC TF minus TI, and that's negative, because that one's now losing. So we're saying this is gained, this is lost. Yep. Follow me so far, Austin? Cool. All right, what's the mass of the thing that gained? This one gained. So the mass was 50 multiplied by 4.18 multiplied by TF. I don't know what the final temperature is. Minus TI. Well, it started at 25. Is equal to negative. I'm going to put that negative in a different colour just so we don't forget it. Because at this stage, the way we're just solving it here, this is important. Negative. Mass of the losing, the thing that loses is 100 grams. 100 multiplied by 4.18 multiplied by the final temperature. What's the final temperature? We don't know. Minus initial temperature started at 90 degrees. All right. Then we just multiply all that out. Solve for TF. Have a crack at that. You want to have a go by yourself? No. What was that number? That was 37,620. Okay, this is where that negative comes in. Very important. Look, if I make that negative now and I get rid of these brackets, that's negative, and that's positive. Yes? Follow me so far, Jade? That's right. It's a little bit messy through here, the multiplying, expanding, rearranging, changing sides, changing signs. 627 TF equals 42,845. Uh, 68.3. So far, so good.
Yeah, so I'm just wondering about your calculation. Could
No,
have made
they're
it
right.
simple.
Yes.
You
Yeah,
didn't
that's
see.
fine.
You didn't see. It's the same. You cancel that.
Yeah, right. Yes, you could have. But that will work at the moment because we're doing two waters.
Yeah, exactly. When the C's constant.
Okay, so we're going to put it here. Method 1. And then, actually, we won't call that method 1. We're going to call it something different. Here we go.
I'm calling 0. Oh, well, STEM is my favourite job.
Yeah, damn straight it is.
Right, well, that's so good. There's Jacko throwing a chemical.
This is the way I do it. Then I'm going to do the Jackson method.
I like that one.
That's why you do these ones, you know. Moonwalk. That's what his channel should be called, right? If he makes a YouTube channel, it should be called The Moonwalk.
Why?
The Jackson, Michael Jackson.
That's.
Oh, it's like an onion, there's layers to it. Right.
Jackson. You idiot James. Ian Jackson.
Anyway,
Yeah, actually, or it could be that, couldn't it? It could be Jackson, Ian Jackson. Oh, this is getting video too. No one should. Alright, let's look at the Jacko method. In his method, he makes some assumptions here. That his assumption is this: delta T must always be positive. Delta T must always be positive. What he's going to do is eliminate this. He's going to eliminate the need for that negative in there that can get confusing if you don't put it in the right spot, it can get lost. And then your answer's wrong. He's going to say this. That's not what I said. I said Q equals negative Q. He's going to say that the two Q's are the same. A positive must equal a positive. So he's saying that one Q is equal to another Q. And to do that, when we rearrange this formula here, what we're going to do is this. We're going to say MC delta T is equal to MC delta T. Well, that's easy. But if I'm going to say that this, let's make this the gain, and this is the loss. The one that loses heat. So I started with a block that was at 90 degrees Celsius. What is its final temperature going to be? Less than that. Let's make a guess, and let's say its final temperature is 10 degrees Celsius. What did it start as? 90. Delta T is equal to 10 take 90 equals negative 80. What he's saying is do it this way and go and get rid of that and swap it the other way around and say, in this case, I want it to be positive, so I'm going to say delta T, in this case, is going to be the initial minus the final. Whoops. Because it's losing heat, because it's going to be less than what it started, I'm going to switch them around so I get a positive delta T. And if you do that,
can you do that?
in this case you can, because one is actually losing the heat out of it. So in this case, it's now going to equal a positive 80. Right? And for the other one, this is for lost heat, so minus Q. Okay? And for the gain heat, which is positive Q, it's going to be delta T is equal to TF minus TI. What is the final temperature? We shouldn't have gone down to 10, by the way, in that example, because now that was going to be less than the first one it started at, and so that's obviously not possible. Yeah, think about what I just said then. I've given you an example where the final temperature is 10 degrees, which is lower than 90 and 25. That can't be possible if you mix those two together. Yeah, so pretend that that question is not existing at the moment. Pretend that this one was maybe 0 degrees Celsius just for now. All right, the final temperature, an initial, well, it's going to be, the final is going to be somewhere, say about maybe 20 degrees Celsius, and the initial is 0, and so you end up with a positive value again. So both of those delta T's are now positive values. And if you work on that, if you always assume that delta T must be always positive, and organize your change in temperature so that both of them are positive, figuring out which one's going to lose heat and switching it around to Ti minus Tf instead of Tf minus Ti, it will work out. Let's go and do it. The gain is 50 grams. 50 times 4.18 multiplied by the change in temperature. Well, it went from, so it's going to be, what did I say, Tf, this one's gaining, so it's going to be Tf minus Ti minus Ti, which is 25, is equal to 100 multiplied by 4.18 multiplied by Ti minus Tf. And I'll just put T's in there now. I'm saying T is that final temperature. That subscript is used for T for final temperature. If you're going to work all that through, guess what answer you'll get? And it's the same. Personally, I don't care which way you do it. Jacko does the one on the right. He'll give you the same answer.
Yeah, the exact same work as well. The negatives just carried through that bracket.
Right.
Completely.
It's the initial phase that I used to get confused with, of the delta t, both, hang on, what, where? And then making sure I translated that into the problem correctly. Otherwise, if you just use a negative, it will still work. You can just use TF minus TI every time, but you have to carry that negative. But Jacko will use the one on the right. So if you want to get more familiar with it, do that method. Oh, there's the two methods.
Oh,
I do so.
Can't see now.
thank you.
Follow that, Austin? Yep. Jordan? All good. Hayden? All good? All right, now Ryan said a second ago you can go and rearrange these formulas here and here, and you can eliminate C out of those formulas. And yeah, you can, when the C is the same. And in this case it is, because we're looking at the specific heat of water in both circumstances. Let's go now look at an example where we're going to put a block of metal into water, in which case you won't be able to do that. Oh, there's the answers. I'll give you this slideshow too if you want it. Next question. There we go. I want you guys to now work through that problem together. This here is sort of what we're talking about in terms of the Jackson method. That should be like a law now, should it?
Yeah.
It'll be the -1 law of thermodynamics. It's before the zeroth law.
It's not really positive. It's not really negative positive. It's just saying negative is a
But we'll pretend it's. Because it's. Well, this one. Sorry, 627 times 10 is equal to that.
Yep.
And that's divided by 627.
Oh.
Haven't got this one together, guys. We need to work together on it.
Yeah, like,
Whoa, 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 did you just make a racist joke?
Shut up. You said black people can't stay. Shut up. No idea.
I think it says chop.
TMZ, your phone fell over.
Thank you. Can you just turn it off and off while I stop the video?
Yeah.